Thermodynamics is the branch of physics that deals with the relationships between heat, energy, and work. It is a fundamental area of physics that is essential to understanding many natural phenomena, including those that occur in engines, power plants, and other types of machines. The basic principles of thermodynamics can be summarized as follows. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transferred or converted from one form to another. The second law of thermodynamics, also known as the law of entropy, states that in any energy transfer or transformation, the total entropy, or disorder, of the universe always increases. The third law of thermodynamics, also known as the law of absolute zero, states that as the temperature of a system approaches absolute zero, 0 K or minus 273.15 degrees Celsius, the entropy of the system approaches a minimum value. Thermodynamics is based on the fundamental laws of physics, namely the laws of conservation of energy and conservation of mass. In thermodynamics, the main focus is on the energy of the system, and the main goal is to understand how energy is transformed between different forms such as heat, work, and internal energy. Thermodynamics is used in a wide range of applications, including in engines, power plants, refrigeration systems, air conditioning, and heat pumps. There are several key formulas in thermodynamics that are commonly used to calculate various thermodynamic properties and relationships. Some of the most important ones include the ideal gas law, PV equals nRT, where P is pressure, V is volume, N is the number of moles of gas, R is the ideal gas constant, and T is temperature, in Kelvin. The work energy theorem, W equals delta E, where W is work done on or by a system and delta E is the change in internal energy of the system. The enthalpy-entropy relationship, delta H equals T delta S, where delta H is the change in enthalpy, a measure of the total energy of a system, and delta S is the change in entropy, a measure of the disorder or randomness of a system. The Carnot efficiency formula, eta equals 1, Tc/Th, where eta is the efficiency of a Carnot heat engine, Tc is the temperature of the cold reservoir, and Th is the temperature of the hot reservoir. The Clapeyron equation, dP/dt equals delta H/RT squared, where P is pressure, T is temperature and R is the ideal gas constant, and delta H is the change in enthalpy in process. The Joule-Thomson coefficient, mu equals 1/P dt/dP_H, where P is pressure, T is temperature and mu is the Joule-Thomson coefficient, which is related to the change of temperature and pressure when a gas is expanded or compressed adiabatically. These formulas are just a few examples of the many that are used in thermodynamics to calculate various properties and relationships. One example of how thermodynamics is used in real-world applications is in the operation of a heat engine. The most common type of heat engine is the internal combustion engine found in automobiles, but other types of heat engines include steam engines and gas turbine engines. A heat engine operates on a cycle, in which it alternately absorbs thermal energy from a high-temperature source, such as burning gasoline in an internal combustion engine, and rejects thermal energy to a low-temperature sink, such as the coolant in a car's radiator. During this cycle, the heat engine converts some of the thermal energy into mechanical energy, which can then be used to do work, such as turning the wheels of a car. The efficiency of a heat engine is defined as the ratio of the work done by the engine to the heat absorbed from the high-temperature source. This efficiency is limited by the second law of thermodynamics, which states that in any energy transfer or transformation, the total entropy, or disorder, of the universe always increases. One of the most efficient heat engine is the Carnot heat engine, which operates between two temperature Tc and Th. The efficiency of this engine is given by the Carnot efficiency formula, eta equals 1, Tc/Th. For example, if a heat engine has a high temperature source of 800 K and a low temperature sink of 300 K, its maximum theoretical efficiency according to the Carnot efficiency formula would be 1 to 300 800 equals 0. 625 or 60.